There's a world in our own solar system that humanity has seen in astonishing detail and still cannot truly reach. It is not orbiting another star. It is not hidden beyond the edge of the galaxy. It is Pluto, a frozen world so distant that even our fastest successful mission needed almost a decade to arrive. And when it finally got there, it could not stop. It had only a few hours to look before racing onward into the darkness. That is the part most people miss. New Horizons did not explore Pluto the way orbiters explored Mars, Jupiter, or Saturn. It performed a single, breathtaking flyby. It arrived, photographed the surface, sampled the atmosphere, collected everything it could, and then disappeared beyond the system. Humanity crossed billions of kilometers for one brief encounter because stopping at Pluto was far harder than reaching it. Pluto's orbit is enormous and highly elongated. Depending on where Earth and Pluto are positioned, the distance between them can exceed 7 billion kilometers. Even at more favorable alignments, the journey stretches across a scale that makes Mars seem nearby. Jupiter is already difficult to reach. Pluto lies many times farther away. NASA built New Horizons around one overriding requirement: speed. Every kilogram mattered. The spacecraft had to remain small enough to launch at extreme velocity while still carrying cameras, spectrometers, computers, transmitters, heaters, and a nuclear power source. When it left Earth in January 2006, it became the fastest spacecraft ever launched directly from our planet at that time. It crossed the Moon's orbit in less than 9 hours. Apollo astronauts needed about 3 days. Yet New Horizons still required 9.5 years to reach Pluto. For most of that journey, the spacecraft slept. Major systems were powered down to conserve energy and reduce wear. The mission team periodically woke it, checked its health, corrected its trajectory, and returned it to hibernation. For years, one of humanity's most advanced machines coasted through the outer solar system in near silence. Then, in July 2015, Pluto transformed from a blurry point into a world. The first close images revealed mountains made of water ice, vast plains of frozen nitrogen, layered atmospheric haze, possible cryovolcanoes, and the brilliant heart-shaped region now known as Tombaugh Regio. Pluto was not the dead, featureless ball many had expected. Its surface was active, diverse, and geologically young in places. New Horizons had reached a world full of questions, but it could not remain there to answer them. The spacecraft passed Pluto at roughly 50,000 kilometers per hour relative to the dwarf planet. It could not turn around. It could not enter orbit. Mission controllers could not decide to revisit an interesting feature or change the plan after seeing something unexpected. By the time the first signals describing the encounter reached Earth, New Horizons was already millions of kilometers farther away. The reason was simple. Speed had made the mission possible, but speed also made stopping impossible. To enter orbit, a spacecraft must reduce its velocity until the gravity of the destination can capture it. At Jupiter, enormous gravity helps. At Pluto, gravity is extremely weak. Pluto has only a small fraction of Earth's mass and about 6% of Earth's surface gravity. The spacecraft arriving at interplanetary speed simply flies past unless it performs a massive braking maneuver. That maneuver would require an extraordinary amount of propellant. The problem becomes brutal because of the rocket equation. To slow a spacecraft, engines must expel propellant, but propellant has mass. Carrying more propellant makes the spacecraft heavier, which means more propellant is required to accelerate it from Earth, and more propellant is then needed to slow that additional mass at Pluto. The solution grows the problem. A Pluto orbiter using conventional chemical propulsion would need to carry an enormous fuel load for years. Tanks, insulation, valves, pressure systems, heaters, and redundant controls would all have to survive nearly a decade before performing the most critical burn of the mission. If the engine failed after billions of kilometers of travel, the spacecraft would simply rush past Pluto, just as New Horizons did. Engineers could choose a slower trajectory to reduce the required braking, but a slower journey might take decades, increasing the chance of component failure while making the mission harder to fund, operate, and staff. Scientists who designed the instruments could retire before the spacecraft arrived. This is Pluto's central paradox. The faster you travel, the harder it becomes to stop. The easier you make the arrival, the longer you must wait to get there. Even if that paradox were solved, operating near Pluto would create another set of problems. At the time of the New Horizons encounter, a radio signal needed roughly 4.5 hours to travel one way between Earth and the spacecraft. A command and response could therefore take around 9 hours. No one can steer a Pluto mission in real time. Everything must be planned in advance. New Horizons carried out its flyby autonomously. It followed a sequence of commands uploaded before the encounter, pointing its instruments, collecting measurements, turning, photographing, and storing data without immediate help from Earth. Mission controllers could only wait and hope that the spacecraft had performed correctly. At Pluto, exploration resembles sending a photographer into an unknown landscape with a locked schedule and receiving the results hours later. That communication delay can never be engineered away. It comes from the finite speed of light. The connection is also incredibly weak. New Horizons transmitted data at only a few kilobits per second. A modern home internet connection can be hundreds of thousands of times faster. The complete Pluto flyby dataset took about 16 months to reach Earth. A future orbiter would gather far more information than New Horizons. That creates a difficult choice. Either the spacecraft stores vast quantities of data and spends years transmitting them, or it carries a larger antenna and a more powerful transmitter, increasing mass and energy demand. Energy is another severe limitation. Sunlight near Pluto is roughly 1,000 times weaker than near Earth. Solar panels that produce useful power in the inner solar system become enormous and inefficient at that distance. New Horizons relied on a radioisotope thermoelectric generator, which converted heat from decaying plutonium into electricity. The entire spacecraft operated on roughly the power demand of a few household light bulbs. That tiny supply had to run the computer, scientific instruments, communication system, and heaters protecting electronics from the deep cold. A Pluto orbiter would need more instruments, more processing power, stronger communications, and years of orbital maneuvering. A conventional radioisotope generator might not be enough. A compact nuclear reactor could provide greater power, but that would add mass, complexity, shielding, cooling equipment, regulation, and political risk. This is why nearly every serious concept for a future Pluto orbiter eventually reaches the same conclusion. Chemical rockets and small radioisotope generators may not be enough. Pluto probably requires nuclear propulsion, nuclear electricity, or both. Nuclear thermal propulsion could heat propellant using a reactor rather than chemical combustion. That would provide better efficiency and potentially shorten the journey while preserving more fuel for braking at Pluto. Nuclear electric propulsion could use a reactor to power ion engines. These engines produce very little thrust at any single moment, but they can operate for months or years, gradually building enormous velocity and later applying sustained braking before arrival. On paper, this is exactly the kind of capability a Pluto mission needs. In reality, no full nuclear electric system at the required scale has flown. Nuclear thermal propulsion has been studied and tested on the ground, but modern flight-ready systems still require years of development. Engineers must build reactors that remain safe during launch, survive deep space, operate reliably for decades, and function without maintenance billions of kilometers from Earth. The technology problem is matched by a political one. Launching nuclear material requires safety reviews, environmental assessments, public acceptance, specialized facilities, and sustained funding. A Pluto orbiter could take 5 to 10 years to design and build, another 5 to 10 years to travel, and many more years to operate. The people approving the mission may not be in office when it arrives. The engineers who begin the project may not be working when the first close orbital images return. Pluto demands commitment across generations of budgets, administrations, and scientific teams. Human travel is even more distant. A crewed spacecraft would need living space, food, water, radiation protection, medical facilities, exercise equipment, waste systems, spare parts, and life support, capable of functioning for years without rescue. Every additional kilogram would require more propulsion. More propulsion would require more fuel. More fuel would require a larger spacecraft. The mass would spiral beyond anything humans can currently launch or assemble. The psychological challenge would be equally severe. Astronauts would spend years in isolation with communication delays measured in hours. There would be no emergency return. A serious failure near Pluto would unfold farther from help than any human being has ever traveled. So why keep trying? Because New Horizons revealed just enough to show how much remains hidden. Pluto's nitrogen ice appears to convect like a slow-moving glacier. Mountains rise several kilometers high. The atmosphere forms delicate blue haze layers. Charon, Pluto's largest moon, carries enormous canyons and signs of a violent geological past. 4 smaller moons move through the system in complex, sometimes chaotic rotations. A flyby provided snapshots. An orbiter could watch seasons change, map the entire surface, measure the interior, track the atmosphere, study interactions between Pluto and Charon, and repeatedly visit the smaller moons. Humanity once had an earlier chance. During the 1960s, engineers discovered a rare alignment of Jupiter, Saturn, Uranus, and Neptune. Spacecraft could use each planet's gravity as a slingshot toward the next. A proposed Grand Tour mission might have included Pluto. Budget pressure reduced that vision to the Voyager program. Voyager 1 could have been directed toward Pluto after Saturn, but scientists chose a close encounter with Titan instead. Titan's thick atmosphere and organic chemistry made it an extraordinary target, and the decision produced remarkable science. But Pluto was left behind. For decades, mission concepts appeared and disappeared. They were too expensive, too heavy, or too difficult to fit within NASA's priorities. New Horizons finally succeeded because it was built as a lightweight reconnaissance mission rather than an orbiter. It gave humanity its first look. It also proved that a first look was not enough. A future orbiter could also reveal whether Pluto still hides an internal ocean beneath its frozen crust. It could determine why Sputnik Planitia remains so smooth, how nitrogen ice circulates through the basin, whether the suspected cryovolcanoes ever erupt, and how rapidly the atmosphere changes as Pluto moves farther from the Sun. Those are not minor details. They could reshape our understanding of how small icy worlds remain active for billions of years, and whether similar hidden processes operate across the distant Kuiper Belt even now, unseen. Pluto is not unreachable forever. Better reactors, nuclear engines, autonomous navigation, in-space assembly, and improved communication could eventually make an orbiter practical. None requires magic, but all require development, testing, funding, and patience on a scale that has not yet been committed. That is the honest reality. We can see Pluto, we can measure its orbit, we can reconstruct its surface and atmosphere from one extraordinary encounter, yet we cannot currently send a spacecraft there, slow it down, place it into orbit, and operate it for years without accepting extreme cost and risk. Pluto marks a boundary between the solar system we can visit and the solar system we can truly explore. New Horizons crossed that boundary for a few hours. The next mission must cross it and stay. Until then, Pluto remains frozen in the distance, not because it has nothing left to reveal, but because our technology is still catching up with the questions waiting there.